In this video, I'm gonna do a walkthrough through examples of chapter 3 of the Grokking Deep Reinforcement Learning book. This chapter is about the balance between short-term and long-term rewards. In the previous video, I gave the instructions of how to start the Docker environment to run the Python examples in Google Colaboratory, but I'm gonna include the link to this page that has the instructions how to do it. And let's go to the chapter. So this is the book again, and we're gonna cover chapter 3, which is balancing immediate and long-term rewards. So the chapter is basically going through some examples, some basic examples for reinforcement learning, very easy to master. Is basically the purpose is to illustrate some basic techniques of reinforcement learning, such as getting the Q value, the value function, the Q function, and also the policy to maximize the long-term reward of an environment. So let's go there. So this I'm gonna put also this link into the description, so you have all the examples in here. So first, I'm gonna create a new notebook just to do it little by little. There's gonna be first we're gonna set the randomization seeds. We're gonna use OpenAI Gym for this, NumPy as well, and TQDM, among other things. So yeah, this is importing the stuff that we need. So I'm just gonna run it. We're gonna have a few methods that we're gonna use over and over in this chapter. Some of them are for printing the value function, Q function, policy. Others are for computing the value function based on an environment and based on other things, or computing the Q function, computing the policy, the optimal policy, things like that. Okay, so the first one is to print the policy. So let's put it here. So you can see that we're iterating. Well, this is for printing. We have the P. The P is the environment. This is the Markov decision process, the MDP. If you see the previous video, you're gonna see that the environments. You're gonna see an environment in a moment. It's basically a nested dictionary that has the list of states, and for each state you have a set of actions, and for each action you get the corresponding probability of going to a next state and the reward for it. You have all the information of the Markov decision process in there. So the P is basically the policy, and based on that policy, it's gonna print the policy. This is just gonna print it. So if you're in this is basically if you're in the final, if you're done in the terminating state, then you're just gonna print empty, and otherwise you're gonna print the state and the corresponding action. So you're gonna go through each state of the Markov decision process of the environment, and just gonna print everything, the policy basically, because for each state there's an action. That's a definition of a policy. Okay, you're on a given state, I'm gonna take certain action, so that's what it's gonna print. Okay, so the next one is to print the state value function. The value function is the V. The V and P is just taken just to know the states. So you can see that it's going to iterate through all the states, and for each state it's going to just print the corresponding value, the state and the corresponding value. So there's gonna be some rounding here involved, but you're just printing the value. The value is basically the expected long-term reward for a particular state, and I'm gonna show a formula for that. So here is the value. The value formula is basically the expected value. So given the state, is the expected long-term reward that you're gonna get, and that depends on the policy, because the policy usually takes one and only one action per state. Okay, given that action, and the given state, you have a probability of landing to another state. An example of this is the environment that we're going to see in this video, which is the slippery walk, or the frozen lake example, in which given an action, it doesn't guarantee that you're going to go in the direction that you want to go. You might go in the direction that you want to go, but also you might go in other directions. So basically you have to sum all those probabilities. You have to weight those probabilities, multiply the probability against the corresponding reward of the next state. So basically you add all those probabilities, and that's going to be your expected long-term reward for that particular state. Okay, so that's what the value function is. Let's go back to the scripts. Okay, so now the next one is the action value function. The action value function is similar to the long-term reward, but is given a state and an action taken, what is my long-term reward, and that can be used as a policy. If you take the maximum action based on the Q function, I'm going to show the Q formula, is this one. So it's basically the expected value given a state and an action, that will be the reward at the given time, but also you have to add the rewards in the future, which includes the discount, because the longer it takes to get the reward, you should not be getting the same reward sometimes, because if this coefficient is 1, then you just add up all the rewards. So basically it's the reward given the state and the action. So yeah, so basically it's gonna iterate through it should iterate through all the states and action, but no, it's doing something different to print it. It's basically gonna convert it into a table and just concatenate the values and just tabulate and print it. So that's all it's doing. It's not really important. You're gonna see it in a moment how it goes. Okay, so so this one are gonna be used to evaluate how good the policy is. So given the policy and the environment, I want to know what is the success rate of that policy. So the policy, when you use it in an environment, could reach the desired goal. In that case, you have a success. Or it could reach a terminating state in which you don't reach the goal. That is failure. So for example, in the frozen lake, the environment that we're going to use in this video, you're going to see that if you fall into a lake, then you fail. So that's not success. If you reach the final cell, then you reach the goal. So that's what it does. It basically, you have a number of set of episodes, and then for each episode you have a maximum number of steps, and for each step you're gonna, given the state is gonna give you the action, and you apply the action on the environment. The environment is gonna give you an X state and an indication that you're done. So once you're done, you exit the while loop, and then you check if your final state is equal to the goal state, and then you add the result. At the end, you sum all the instances where you landed into a goal state and get the divided by the total number of results. So that's give you the success rate. So the next one is similar, but is to also to evaluate the effectiveness of the policy, but is to get the reward. So again, you get the policy, you iterate through a number set of episodes, and for each episode a number set of steps. Use the policy, given the state, give me the action, apply it on the environment, get the reward, and now I get the reward. Notice that the reward for each episode is gonna append a 0 here. So it's gonna be a different value for each episode. So for each episode, the last element, I'm gonna accumulate the reward in there, and then take the average between all episodes, and that's gonna give you the average reward over all episodes of that particular policy applied to the given environment. Okay, so with that, now we can start playing with the environments. Let's start first with the slippery walk. The slippery walk is basically like 5 or 7 cells that if you go through extreme left, you lose. If you go through extreme right, you win. But it's slippery. So of course, the greedy policy of going right is always good. But when you take the action to go right, you might go right, but also you might go left. So it depends on the environment. If the environment is kind of a bad environment, would be that you have equal chance going right or going left. In that case, maybe the action that you take doesn't matter. But sometimes if you have a higher percent of going the way that you want to go, then I guess the policy in this case, in this very easy environment, it will be going right. But then we're going to see the frozen lake, which basically you have possibilities of going upwards, downwards, left, right, and you can land into a lake, as I mentioned. That is more complicated to optimize than this one. So okay, so for a moment, let's see how it goes with this very simple example. So we're gonna get a very bad policy, and you can see that we captured the policy into a lambda. So basically, the policy is gonna be for state 0, 1, given the state, we always gonna go left. And then we create a dictionary. That dictionary is basically the key is the state, and the value is the action. And then the lambda is gonna give the state and just evaluate the dictionary and get the action. Okay, so now we're gonna print the policy, we're gonna print the probability of success, the functions that we just declared, and then the mean return. And we're gonna expect that this is gonna be real bad. But first, just so to take a look at the environment, I'm just gonna print it. You're gonna see here that we have a set of states from 0 to 7, and then for each state you get a, let's say for example state number 3. Let's just grab it. We have a set of actions, for example action number 0, action number 1, so you can go left or you can go right. Let's say that we go right. Now you have a probability of 50% of going to state number 4, or of actually going right, but you also have 33% chance of staying where you are and 17% chance of going left. And there are not terminal states near of them, and this is the reward. There's no reward. The only place where you have reward is in the final one, which will be the fifth one. You can see the reward here, and that's where you win. Okay, so now let's evaluate this bad policy. So we have 7% of success and very bad reward. I would expect a 0% of success, but since it is slippery, there's a slight chance of landing into the goal, even though you don't want to go to the goal. So that's the nature of the environment. Okay, now we're gonna create the value function. This function is to create the value function. So let's take a look. So here, basically what we do is create the value function based on the policy. So we're gonna create a value function the same size of the number of states. It's gonna be float values. So we're gonna create this one, and then we're gonna evaluate for each state. We're gonna iterate through all the possible. For example, let's say that we're, as I mentioned before, let's say that we are in state number 3, and then for the particular policy here, let's say that we take this is the same state. It's actually the same state. So for that particular action, we get three tuples within this list. There's a list of 3 tuples. And then for each tuple, we're gonna get the probability. We're gonna get the next state, the reward, and if it is done or not. And with that, we use the previous value function. In this case, the previous value function is 0 initially. Notice that at the end, when we finish, we copy the current v into the previous one. So we're gonna use the previous one to compute the next one, and we're gonna quit. We're gonna quit when the previous one minus the current one is less than a threshold. So basically with that, this is basically the decay. So if we put 1, we don't have a decay of the reward in the long time. So usually you want to, sometimes in some cases it's desirable to decay the reward to put some pressure to the agent to finish as soon as possible. Okay, so this is the reward at the given state, and this is the long-term reward. And of course, we don't want to count it if we are in that terminal state. And then we have to multiply by the probability, because if you remember the formula, you can see that we have to weight the probability by the reward so you can get the expected value. That is the expected value formula. So with that, we accumulate, and then we get the expected value for that particular state. Okay, so let's we want to see how fast does this converge. So let's modify it a little bit, just to measure the number of steps, and then for each step I want to print the v function. Okay, let's increment by 1. Okay, and also let's print the v to see how it goes. Okay, now let's remove this, and we're gonna compute the value function for the environment that we have, the policy, the bad policy. We're not gonna compute the value function. Okay, notice that it takes a lot of steps to compute it. But one interesting thing to note in here is, as the author writes in the book, is that initially, if you notice, there's only reward on state number 5. So there's no awareness in the other states of how much reward I get in this state. But then, as the value function gets iteratively updated, then the reward gets propagated until you get a reward everywhere, and at the end it's gonna converge, and at this point it didn't change much, so we terminate in 103 steps, and you can see at the end the values. Notice that the higher reward should be near the goal. The farther you are from the goal, the less reward you expect from that state. That's because you don't want to be in those states, you want to be closer to the goal. Okay, so let's remove this. We don't want to print v. We just want to print the number of steps that we get at the end. So let's just print it. Okay, so we finish in 103 steps. Okay, now a policy improvement is to compute the Q value. The Q value is similar. So let's take a look. The Q value is going to be useful to get a policy, a new policy, because it can help us getting the maximum out of it. Okay, so you can see here, we are not returning the value function this time, we're returning a new policy. So the input is going to be an environment, it's going to be the value function, which we already have, and then we're going to compute the Q. The Q is basically the long-term reward for a particular state and a particular action. So we iterate using the environment through every state, and using the environment you iterate through all possible actions for that particular state. And then the environment is going to give you all the tuples. We're going to iterate to all the tuples that we have, and the expected value, again, the formula is weighting the probability of that particular action and that particular next state, because given the action also there's a probability for taking for actually landing in the next state. So we weight that, and then this is the reward of the state, and then the decay of the reward, and we use the value function to estimate the long-term reward. And of course we don't want to count when we're done, and we accumulate that to get the expected value of the Q function. Finally, we get the argmax. We're going to make a dictionary out of this. So basically we enumerate basically when we do this we get the maximum. Let's first do this outside so it can be clearer. Okay, let's see if we can execute this. Okay, I'm gonna correct this. Okay, I just needed to put the gamma in here and also correct the indentation, and now we have the Q. Okay, if we do this, the argmax, let's take a look at the Q. It's gonna be clearer like this. So for this we have the 7 states, and for each state we get the expected value, long time reward for that particular action at the given state. Notice that as in the value function, the best rewards are where we're closer to the goal state, which is the final one. But notice that the action, the right hand, the one in the right, is giving us the best reward. So if we take this is gonna take remember Python is 0 indexed, and this is gonna take the dimension number 2, which is the action. So it's gonna give you, for each state, it's gonna give you the maximum, the key of the maximum value. In this case, for example, the maximum value is this one, so the key is number 1. For here it doesn't matter, so it gives you 0. For this is 1. For this is the maximum value, so the key for that maximum value is 1. So it's 1. It's giving you the best action for each state. So that's what argmax is doing there. And when we enumerate, we're gonna get the state and the action, the state and the corresponding best action. So that basically gives you a dictionary. And then we have a dictionary with the best actions for each state, and that's the policy. And then with the dictionary, the lambda is going to give you a state, and it's going to give you the action, and that lambda is going to be your policy, your new policy. Okay? So let's remove this. Okay, let's run it. Now we're going to use the policy improvement, and we're going to provide the value function, which we need to estimate the long-term reward, and the environment, and this is going to give us a new policy, and it should be an optimal policy. For this case, since the environment is so simple, we basically get the optimum, which is it's going to give a success rate. Notice that we're using the same functions that we declared earlier to get the probability of success and the mean return, and the average return is 0.93 and 93% success rate. So it doesn't get better than this. So let's see what the author does next. So it's gonna do policy evaluation again. We're gonna get the value function. We're gonna get the value function on that particular. So with the improved policy and the environment, we're gonna get the value function and print it out. And notice still we get the same pattern of the best reward being close to the right, but we get more precise value numbers for the value function. And then again, look at this. We are going policy improvement once again, and see if something happens. Nothing is gonna happen. Nothing is gonna happen because we are at 93%, and then we compute the value function again, and with that, it basically the author is trying to get to the point that we converge into the optimal policy for this particular environment, and of course we assert that the improved one and the improve are going to be the same. Okay, and now we're going to use policy iteration, which is another method to get an optimal policy. So in here we get a random actions. So with those random actions, for the number of states in your environment, we're gonna get a dictionary. We enumerate them, we key them value, state action, and then given the state, it's gonna give us the action. So it's gonna be a random policy. And then from that random policy, we are gonna use the existing policy. Initially is the random policy. So given we're gonna create a dictionary, and this is to evaluate, and then we're going to use policy evaluation. Policy evaluation is going to give you the b value, and then policy improvement, the same two functions that we used so far to give the new policy, and it's going to compare the policy. Once the policies are the same, that is given each state the action is the same, then we converge and we just break and return the policy. So we're going to take a look at that. Let's make some small modifications so that we can take a look at the progress. So this is gonna be the dictionary of the new policy. I want to see the dictionary new by. Okay, and I want to print it. Okay, but also I want to see the number of steps that I'm taking to converge. Okay, so Okay, now let's print the new policy. So let's see how the policy converges. Okay, and now we're gonna use policy iteration. We start from zero, from a random policy, so we can just, it just needs the environment to do all this. So it's gonna print the policy, and it's gonna print the probability of success, the mean return, and also the value function for it. So you're gonna see, for this very simple example, we're gonna converge to the same place that we were before. So notice that it's gonna take two steps, because of course it has to converge. The first one is random, and the second one is already the final one. So notice that it's basically the same. It's basically the same. So it's a confirmation for, but notice the number of steps. This is the number of steps to get the value function. For the second time, where we're closer to a goal, it took less to converge to get the value function. Okay. So now let's, of course, the optimal is the same policy. We converge to the same place. So this is a very simple example. Now let's take a look at a more complicated example. In this case, it's the frozen lake. The frozen lake is basically this. You have a grid of 16 states, and you can go up, down, left, or right. And you, of course, since it's slippery, you might go in the direction that you might want to go, but you can also go left, can also go right. And one of the things that the author points out in the book is that if you take the greedy policy to go all the way directly into this place, you're gonna perform poorly, because most likely you're gonna fall into one of those lakes, because it is slippery. There's another policy that is careful, that you take the action with the least probability of landing in one of these lakes, and that one performs better than the greedy. But of course, there are better policies, and the mechanism that we have seen so far are going to help us to get a more optimal policy for this a little bit more complicated example. Okay, so let's go to the script. So we're going to take it from OpenAI Gym, and just take a quick look at the environment. It's way more complicated, but the structure is the same. You can see that we have 16 states, and we have 4 possible actions for each state: up, left, up, down, left, right. And notice that this is kind of an unfair environment, in the sense that you have equal probability of going to other states. You don't have a higher probability of going where you want to go, but still it doesn't go to all states. It's not that unfair. Okay, so let's delete this. And now this policy is a random policy, just a random policy, and we're just going to print it and check out the probability of success. Notice that we're going to use the same functions that we have so far to print, for getting the policy, getting the value, etc., and print everything. Okay, so the random policy is going to give us, and notice that the print policy is going to do a good job of tabulating. And here's the state. So we have 16 states, and initially we take this state takes the action to the right, this one to the left, down, and this is the lake. These empty places are the lake. So basically it's kind of a little bit random. It's basically random, and this is the goal state. And there's 12% probability of a success and very low reward. Okay. Now this is the aggressive one. This is the greedy one. It's gonna try to go to the goal directly. So notice he wants to go here directly. That's the action. Wants to just get into the goal, and performs surprisingly very poor. 5% probability of success and a very low reward. Okay, now we're going with a careful one. Careful one tries to avoid getting into the lake. and notice that it goes left because you don't want to land into a lake. Now you go up, you go down, you don't want to land into a lake. So this one has such a higher probability of success, 52%, way higher, and higher long-term reward. Okay, now we're going to use the policy evaluation to get the value function according to the policy, to the careful policy, which is the best that we have so far. And you can see the closer you get to the goal, the better. And I suppose that this also includes the safety as well, because if the value function models the reward for not falling into a lake and also the reward for going to the goal, then you can go greedy on it, because it's the reward, I mean the value function is modeling both the penalty and the reward. It's modeling everything, so you could go greedy on it. But this environment still is very simple, and you know everything, and you don't have to explore much. In other environments that are more complicated, exploration is important as well. So taking a greedy policy is not going to allow you to explore as much as possible the environment. So later in the book, the author is going to talk about the balancing between exploration and exploitation that is important for larger environments. In here, you know everything, so you can go greedy on this value function. So we're going to continue. We're going to use policy improvement. Again, policy improvement is going to use the value function and compute the Q value. Let's go again just to review. Let's go to the policy improvement. Policy improvement is going to compute the Q function based on the value function. It's gonna compute the Q function, and then it's gonna get the argmax. Argmax is gonna be greedy, so it's gonna get a greedy policy based on the expected value for the state and action. Again, this is modeling falling into the lakes and getting into a goal, so you can go greedy in this small example. So let's see how the policy improvement goes. Okay, so we are here, policy improvement. So given the environment and the best policy that we have so far, we just have to give the value function, which is taken from the careful policy and the environment, and that's gonna give us our new policy. This is gonna be our new policy, and he's gonna call it careful plus. Okay, so this one is gonna do better, 74%. And notice one thing in this environment, there's no higher percent probability of going where you want to go. There's a very high chance of it's very random. So it's 33% equally to go in 3 different directions, and 2 of them you don't want to go. So it's kind of hard to get a high probability of success because of that in this environment. So you're gonna see that it's gonna stall at 74% with 0.74 reward. So now we're gonna create a value function. The value function is gonna give us a better estimate of the value function. Again, the closer to the goal, the higher. Also, I suppose that the closer to the lakes, the lower as well. Okay, now we're gonna just print it. So this is gonna print the difference between the value functions, the difference between the new one and the old one. Yeah, it changed a little. Okay, now we're gonna have an adversarial a policy. That means that you want to drop the agent into a lake by intention. So this should perform very badly because it's just want to throw it into the lake, and with that we get well, as expected, 0% of success and 0 reward. So the author is given that policy, we're going to compute the value, and then we're going to go through policy improvement, and you're going to see that there's no initial progress. But still we're computing the reward based on the reward of the environment. The environment is gonna reward us if we get into a final state, and if it's gonna penalize us if we get into the lake. So basically the value function is still gonna give us some reward. And also there's some randomness. So yeah. So anyway, so we're gonna get the policy improvement based on the new value function. The policy improvement is not adversarial anymore. It's gonna be based on the Q value. It's gonna take the argmax and it's gonna take the action that maximizes that reward, although we don't have much information. And initially it's gonna remain bad, 0% still, but we keep doing it. We feed the previous policy to get a new value function, and as we get a better estimate of the long-term reward for each state, we can get a better policy based on those rewards. And we can see that it's still there. It takes a few iterations. So basically the point that the author is trying to make is that if we keep iterating between getting the value function and getting the policy based on the Q function and the greedy argmax, then eventually you're gonna get into an optimal policy. It takes a while, but you're gonna get there. And here you are at 20%. We keep iterating. So he's gonna put this into a for loop eventually. I'm just illustrating manually. And yeah, now at this point we are doing the same all over again. Now we are close to the end, 73%. I'm not gonna go through the rest. Eventually it goes to 74%, and yeah, he keeps going. It basically converges to 74%. Okay, now the policy iteration is gonna do that automatically, what we just did. So in here, no, this is another thing, my bad. Okay. Yeah, that is precisely because we already did it. If you go to policy iteration, we already declared it. So basically it's gonna have a random, this is better than the adversarial policy. So it's gonna do policy evaluation, the value. We're gonna take policy improvement to compute the greedy policy, and then it's gonna keep going iteratively until we converge into a policy that doesn't improve anymore. So that's what policy iteration is doing. So we're gonna apply given the environment and a long-term reward discount of 0.99. We're gonna get the value function and also the best policy, and then we're gonna print the value function and the probability of success and print the policy. Okay, so it takes. Notice that at the beginning computing the value function is very fast, but as we progress, computing the value function takes longer. And it took 7 iterations of what we just did to get into the same place. 74% of success and the same reward. And you can see a policy in here is kind of protecting itself, protect yourself, and then go right. So yeah, it's basically careful while you're close to the lakes, and then gets greedy when you're close to the goal. That's about it. Okay. Yeah, so this is another environment. Okay, what the author is doing here is interesting. It's basically notice that the in policy iteration is kind of a little bit inefficient because we call this function to compute the value function and then compute the pi in separate functions, and if we merge it, then it can be less mood, reduce the mood a little bit. So if you multiply all of this, you're gonna see that you can have maybe 2,000 iterations or something like that. So now this one is gonna be a little different. It's gonna do everything together. So let's take. So given the environment, we're gonna assume put 0 in the long-term reward function, and then we're gonna iterate. We're gonna have a queue also is zeros given the number of states and the number of actions. This is assuming that all actions, all states has the same number of actions, and they iterate through all the states, actions, and use the environment to get the tuples, and use the same formula. Notice it's the same formula that we use to compute the Q value function in the policy improvement function. It's the same, and then we converge when the value function is the same as the so basically it's converging. Here it's taking the maximum value. The maximum value of the q should be equivalent to the value function. So value function is assuming that you're taking the maximum action. Okay, so when that converges, then you break, and then the value function becomes this, the maximum value of the q function, given you take the best action for each state, and that gives you the best value, the best reward, and that's basically your value function. And then given the q, again you do the same that we did in policy improvement. We take the argmax, we take the best action for each state, and that gives us our policy. It's our greedy policy. Okay, so let's see how much it takes to converge. So yeah, so let's just print it out here. Okay, and print the v. Okay, let's just run it, and then we're going to use the value iteration. We're going to print the policy that it's going to give us, and the probability of success, the mean reward, and let's see how many steps it takes to converge. Yeah, again, the propagation of the value is very similar to what we saw. We don't actually need to see that. So I'm just gonna put it down here. Yeah, so it took maybe 1/2 of the iteration. You notice that it's more efficient to do it this way. So this is a good way, given that you don't know for the environment the long-term reward. You just initialize it in 0 and let the environment give you the reward, and you iteratively update the q value function, then the value function being greedy, and then take the greedy. But this works for this simple environment to get the optimal policy. And something happened in here. Let me see what happened. Yeah, what happened was that I did not use the right environment, so I'm gonna just put another cell in here, load the environment, the slippery walk, run it. Yeah, this is a slippery walk. Okay, so it reached the end, but this is not the frozen lake. Okay, so it took 129 steps and it got 93%. This is the same slippery walk that we were using at the beginning, and it got to the optimal solution. But now the frozen lake. Okay, let's go get to the frozen lake, and then let's try the same value iteration and see how many steps we get to take there. Wow, 570 steps, and we got a 74%. We get to the same, converge to the same place, but with a 1/3 of the iterations. So it's much faster. It's a better technique. Okay, and then yeah, this is basically printing the policy, probability of success. We already have that. Yeah, there's nothing new in there. Yeah, so there's other things that you can try in here, but I think that's the most important, and it also includes an example of a Rosser and Norvig grid world. I understand that this should be from the classical artificial intelligence book. Okay, so that's about it. Thank you very much.